All right. So throughout this process, as we go through it, you should notice a couple of shortcuts along the way, which is good. But for at least the time being, we want to get the technique down. So we're applying the difference quotient. It says find and simplify this entire expression for the given functions. All right. It's not itemized like the previous problems where it would say, I'll show you, where it would say first find f of x plus h and then dive into the whole thing. It's just saying go right for the whole thing. You know, like there's no more like kidding around here. We're just diving in like animals. You know, so get rid of the stars here. So the first thing you would do is figure out what f of x plus h is. Because even though the question didn't explicitly say figure that part out, it's in our best interest to do so. So I'm going to take my original function and I'm going to replace every x with an x plus h. All right. And when I do that, it'll allow me to distribute a little bit, not too much. There's not really much to do. The simpler the function that you're working with, the less work you'll typically have to do. All right. So we have negative 2x minus 2h plus 5. All right, that's a far cry from some of the problems we were working on last time, right, for the f of x plus h part. There's no double distributing. It doesn't really get too crazy, all right? But you'll see in a couple minutes how it can get a little bit more elaborate. All right, so we're going to take our difference quotient, the f of x plus h. So this is me just writing the rule, minus f of x all over h. I'm going to substitute in what I just got for the f of x plus h.
Can you just, before you do this, can you just explain that one more time? So you took f of x plus h, and how did you get to?
How did I get this?
Yeah, how did you, please just do that one more time, because I lost this the last class.
Yeah, so what I did is I took the original function, rewrote it, omitting all of the x's. Instead of the x's, I left open set of parentheses. When I'm looking for f of x plus h, all I'm doing is replacing each x in the original function with an x plus h. Then from there, it's a matter of simplifying. So I'm taking this negative 2 and distributing. So negative 2x minus 2h plus 5. All right, but the key is that first step where you take your original function and everywhere you have an x, you swap it out for an x plus h. So then we make this substitution. Since now we know that f of x plus h is equivalent to negative 2x minus 2h plus 5, I can make a direct substitution. All right, so that's just a quick swap out. I also know that f of x, all right, that given function, f of x is equal to negative 2x plus 5. So I could do another direct substitution, but this time in parentheses, because I'm subtracting the entire f of x function, which consists of negative 2x plus 5. I leave the h alone. That's part of the fun. But then it's just a matter of simplifying this. You know, easier said than done, but when you're dealing with a linear equation, that's what we're starting off with here, a linear equation, it should be pretty, I don't want to say easy, but comparatively easy. And it's going to be a lot easier than a quadratic or a cubic, which we'll get to in a couple of minutes. All right, so I have a negative 1 here as a coefficient. I'm going to distribute that through. So I'm looking at negative 2x minus 2h plus 5 plus 2x minus 5 all over h. Now, a good checkpoint in this process would be this step here, or at least what I'm about to do. Your entire f of x should cancel away. If it doesn't, then you made a mistake. Right? So you see how we have the result of this f of x, all this stuff here? That leads to cancellations. This cancels with this cancels with this, and we actually have a pretty simple expression left over. All right, because you're going to be looking at opposite signs when you have your simplifying. All right, so anything that does not have an h attached to it should cancel out completely. You should only be left on the top with terms that have h's attached to them.
Okay, so Professor, you took the yellow, I guess I'm kind of colorblind, the yellow f of x plus h minus the pink f of x. Why did you put 2x plus 5 where the f of x is?
Because that's what they told us it was up here. They said it was negative 2x plus 5.
Okay.
So I made that direct substitution.
Okay, so you kind of took it apart. You took like f of x plus h and you made it, you added the x plus h into the negative 2x plus 5, and then you brought down the negative 2x plus 5 to substitute for the negative f of x. Am I correct?
Right, exactly. Yeah, I brought those pieces in, merged them, and then simplified.
So this is like more like a taking it apart and then putting it back together problem.
Yeah.
Okay, thank you.
No problem. And you'll see, and by the way, that's the solution, negative 2. And so you'll see for linear equations. So for linear equations, the result is always the slope of the original line. All right. So if you recognize something as being a linear equation to get started, you look at it and say, oh, it's a line. Then all you have to do is pull the slope and you have your answer. So you think about a test problem where it just says find the slope of the secant line, which is really what this whole process is. Because remember, don't lose sight of this. I know after you get into all the algebra behind it, it's kind of hard to keep in mind what exactly you're trying to find. What you're looking for is the slope of the secant line on the given curve. If that curve happens to be a straight line, then that slope should be the slope of the line itself. Okay, so it's a kind of nifty little relationship where if you pick up on it, you can save yourself a little bit of time. Unfortunately, that's one of the few circumstances in which you have that advantage. Every other circumstance, you're pretty much locked in for the work. So looking at B, same idea to get started. We're going to find f of x plus h, which means I'm going to rewrite my given function because everywhere I have an x, I'm going to replace it with an x plus h. All right, so I'm rewriting the original function just with an open set of parentheses instead of the x. I'm going to slot into those open parentheses an x plus h. All right, so this is definitely more of a ride because we have to distribute more. There's more algebra to do. But, it's manageable. It's just you got to be patient. You got to take your time with it because if you don't, then you make a negative sign mistake and before you know it, you're in that final step where you're looking to cancel a bunch of things out. It doesn't work out as nicely, right? So negative Instead of x plus h squared, I'm going to write x plus h times x plus h. For this piece, I could just run through with the -2. So -2x minus 2h. And then I still have my -4 at the end. It's really this piece that's the albatross. So what we'll do is apply distributive property, but I'm going to hang on to that negative for a sec. I'm not going to bother with that just yet. I'm going to focus on this product first and then multiply everything by -1. So first, outer, inner, last, x squared. The outer would be positive xh. Inner, you get another positive xh. And then the last would be h squared. We have our like terms. Understood coefficient of 1. 1 plus 1 is 2. So you have x squared plus 2xh plus h squared. And that whole thing is getting multiplied by -1. All right, that's this negative sign. But I'm going to tuck that little 1 in front. And then everything else is going to come along for the ride. All right. Now, it's not a great deal of fun to do this, obviously, but again, procedurally, if you follow the right steps, it's manageable. All right. So I'm going to take that -1, I'm going to run it through. So -x squared minus 2xh minus h squared, and then everything else comes along for the ride again. Ideally, you'd have some like terms, but unfortunately, it's not meant to be for this problem. So we're kind of stuck with this nasty, disgusting expression. But it's only part of it. I'm going to zoom it back in a second. All right. It's only part of our final answer. This is just the f of x plus h part. We still have to get the rest of the difference quotient involved. And that's where some cancellations are going to happen. And then things are going to clean up kind of nicely. Well, as nice as they can clean up. All right. So I'm going to throw in my difference quotient. Minus f of x all over h. Again, this is the rule. I guess I don't need to zoom out too much. So this nasty looking expression that we just came up with, that's our f of x plus h. So this one here, that whole thing, that's f of x plus h. We get a green here. This original function, that's f of x. So when we create our fraction, we're going to start off with our f of x plus h. And then subtract from that the original function, f of x. Going with the theme of breaking it apart and putting it back together. All right. Now, again, I mentioned this earlier, we want to get the skill down, but you start recognizing some things that occur over and over again, algebraically. What you realize, hopefully, and if not, I'll spell it out for you, is that, again, the f of x stuff is going to cancel out. But what ends up happening is every term that has, or that does not contain an h on the top is going to cancel out. All right, so I'll show you the algebra again, but after this, you can start saying, all right, I can start sort of skipping over the algebra in this next step because things are going to kind of work themselves out. So I have a -1. We run through with the -1. We get -x² minus 2xh minus h squared minus 2x minus 2h minus 4. But then you have the plus x squared plus 2x plus 4. All right, that's the result of the distributive property. And running through that distributive property shows that you have opposites. All right, negative x squared, positive x squared. Negative 2x, positive 2x. Negative 4, positive 4. They're exact opposites. They cancel out. Boom, 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 and one final boom. All right, so we have a total of, I believe, 5 booms. So the remaining, and hopefully, oh, I'm missing a boom. Sorry, there's a boom right there. Total of 6 booms. All right, so we have every remaining term contains an H. And honestly, that's how I recognized that I missed one along the way. Because I saw that -2x and I was like, oh, what are you doing there? You don't have an H. You should have canceled. And I realized I canceled the 2x without canceling the -2x. All right, so it's a quick self-checking mechanism there. All right. Now you notice that there's a common H across the board on the top. You can factor that out. When you factor it out, they cancel out completely. Well, not all the H's, but the ones that you factor out cancel out completely. And you're left with the final answer, which is -2x minus h minus 2. All right, and so that's your, I mean, it's not any prettier than any of the other solutions. I mean, the last one, you know, the previous example, that was the nicest one. Part A was the nicest one. But I mean, it's not terrible when you consider what led to it. You look at all this stuff here and all this crazy algebra that happened, and to end up with just this as a final answer, it's actually, I mean, it's not only surprising, but it's actually kind of nice. But then we get to part C. And now the gloves come off. All right, so this one has a cube. So if you think back to what we were doing here, in this step, we had to raise x plus h to the second power. All right, in raising it to the second power, that led us to multiply x plus h times another x plus h, which, you know, was bad enough. We had to do this. If you have a power of 3, you'll have to multiply by another, like the third x plus h. So I'm going to take you through that process, but I also want to talk to you about something called Pascal's triangle. Now, Pascal's triangle is something that you may have experience with, but you may not. All right, so it depends on your background. Some people have seen it before and some people haven't. So I'm going to assume that nobody's seen it and go from there. All right, so, but we could start this problem off the same way we started the previous ones, with a nice f of x plus h, replacing every x in the original function with an x plus h. All right, so all I'm doing is rewriting the original function, swapping out the x for an x plus h. right? Now, that x plus h cubed, we would have to multiply. So there's two ways to handle this. One way would be to say, all right, I'll take that x plus h and multiply it by itself 3 times. Well, multiply it by itself twice because itself counts as one of them. But 3 factors in total. The 4 gets multiplied by the x and then by the h, so 4x plus 4h. And then we have the plus 5 at the end. But this is the elephant in the room, right? The x plus h times x plus h times x plus h, right? It's not pretty, but it's manageable. And when we get to Pascal's triangle, I'll show you a different way of handling it, which some of you will look at and say, oh, that's great. And others will look at and say, I never want to deal with that. Right? But I can tell you that at some point in time in this course, when it comes to Pascal's triangle, you're not going to have a choice. Right? You're going to have to use it. So it's not an optional topic. It might be optional for this particular question, but it won't be optional for other questions down the line. All right. So what we can do is multiply the first 2 factors together. So these 2, for example. Well, they're all the same, so it really doesn't matter which 2 you multiply. Since we've already done that, we figured that out up here. We can steal that answer. X squared plus 2xh plus h squared. We would then have to multiply against the x plus h. All right. So when you're distributing a trinomial against a binomial, this is an old algebra topic, but it's not one that always comes up. So you're forgiven if it's not fresh in your mind. I'm going to give myself a little room. What you do, you just want to have a systematic approach. So what you do is you take the first term of your first expression and multiply it by each term of the second expression. So we'd be looking at x cubed plus x squared h. Then we would take the second term of our first expression and multiply it by each term of the second expression. All right, so 2xh multiplied by x would be 2x squared h. 2xh times h would be 2xh squared. And then finally, we get a different color involved here. I'm going to go with a nice green for those keeping score at home. Then you would take that h squared and multiply that by each term in the second expression. So h squared times x, but I'm going to write that as xh squared because, you know, with the commutative property, you can go in either order. For consistency, because the other one we wrote as xh squared, we would want to write this as xh squared. And then h squared times h would be h cubed. And then everything else comes along for the ride.
Wait, you wrote x squared, it's cubed.
Say it again.
You wrote x squared, but you said it was cubed.
I wrote x squared somewhere.
Yeah, in the
It's
green.
supposed to be h cubed.
Or I'm sorry, h
Oh,
cubed.
thank
I don't
you.
know why I'm saying x. Sorry, it's late.
I don't know why I wrote h squared. So either way, thank you. Yeah, so bring everything else along for the ride and then look to simplify wherever possible. All right, so I have 2 like terms here, xh squared and 2xh squared. I have like terms here, x squared h, 2x squared h. So this would simplify a little bit more, not a whole heck of a lot, but a little bit. The x cubed plus 3x squared h plus 3xh squared plus h cubed plus 4x plus 4h plus 5. All right. It's a little on the rough side, but it's, again, manageable. It just takes a while. The thing that always stings a little bit is when you realize, oh wait, that was just the f of x plus h part. Now I got to do the rest of it. And you're like, dang it, this isn't fun. Right? But when you get used to it, it gets easier. All right, so we go to our difference quotient, the whole shibiggity bangity boom. We're going to swap out the f of x plus h for this expression. And we're going to swap out the f of x for this expression, because those are the expressions that they're equivalent to. All right, but if you remember what I was saying before, the numerator is basically just going to be this, except for any term that doesn't contain an h. So if you get rid of all the terms that don't have h's in them, whatever's left is what your numerator will eventually become. I mean, it's not very algebraic in terms of the methodology, but if you want to get to the answer, I mean, if your objective is to get to the answer as quickly as possible, that's a valid approach. Right? It's a shorthand way of doing it. It's like the equivalent of scratching out notes on a cocktail napkin. You know, if you're just trying to, or, you know, writing somebody's phone number on your hand. You know, you just need to get the information down. It doesn't have to be elegant. You just have to get it down. Right? So from this, we subtract off x cubed plus 4x plus 5. Clean it up in a sec. All over h. All right. So all of these terms, so we start kind of, I don't want to say cutting corners, but we start working a little bit more efficiently. We know from like the last 10 times we've done an example like this, that we're going to distribute the -1 only to cancel these terms out with the ones that don't have h's. So why not just do that in one shot? All right, make your life a little bit easier. That's part of the process when it comes to becoming more efficient mathematically, is recognizing trends and relationships. Once you notice that something always kind of works out the same way, then you start relying on that information. Right? It's kind of like just a very basic example. You know, you could set up a proportion to figure out how much tax you'd have to pay on top of your dinner, or how much tip if you went out to a restaurant. Or you could just take, you know, if it's 20%, just take the number and divide it by 5. That would be your tip, you know, because it's 20%. So, you know, something like that. You know, 10% and double it. You know, you notice those relationships, and once you latch onto that, things get a lot easier. Right. So,
Professor, do you have a place where we can practice these? Because
yeah,
this
up on my
is
website,
like a lot.
Up on my website, there's extra practice and review. It's all there.
And it tells you the answers so that we're not struggling.
Yeah,
Like,
there's answer keys, and also the
Okay.
OpenStax textbook has all this stuff too.
Okay. With
Yeah,
the
it's all-
answers though, right? Because like
With
I
the
struggle with getting the answer and then not knowing if it's right.
Yeah. So in course content, there's an Excel spreadsheet that has the topic and the suggested practice problems, and those suggested practice problems all have answers that go along with them.
Thank you.
Yeah, no problem. So I'm going to factor out the h. So 3x squared plus 3xh plus h squared plus 4. Then we can cancel that h with the one on the bottom. So 3x squared plus 3xh plus h squared plus 4. All right. And so that would be your solution. And like I said, I mean, it's a lot, but it's the same process every time. It's just the algebra that you have to do along the way is a little bit nastier.
So Professor, on the third, it says 3x squared h. So the bottom wouldn't have come 3x squared h, or it would just be 3x squared?
Oh, I kept the h for some reason. Oh no, let's see. Looking here, when I factor out the h, I'm removing this one. I'm removing one of these, so that gave me just an h. I'm removing one of these, so that gave me an h squared. I'm removing this. So then the next one was just canceling. Oops. So then 3x squared. Yeah, the last line is going to be exactly the same as this,
You're just taking out the h.
just without that h here.
Okay, thank you.
Yeah, no problem. All right. So this next little bit here, it's related to something called Pascal's triangle. It's like I said, it's not the kind of thing that you would necessarily think to do for this problem, but, and I'll show you, I just want to double check to see. I do have another problem that involves a cube on the next page, so there is value to it. All right, so I wanted to talk to you about Pascal's triangle really quickly because it's a nice, efficient way of coming up with the expansion of a polynomial without having to do all this algebra, right? So, and what I mean by that is when we had the x plus h cubed, we needed to get to x cubed plus 3x squared h plus 3x h squared plus h cubed. We needed to get to that expansion, but we didn't want to have to do all this stuff along the way, right? Pascal's triangle helps you to avoid that sort of thing, right? So I'm going to show you how to first construct the triangle, and then I'll show you what it means, all right? So first off, if you have an expression, for example, x plus h to the 0th power, right? So raised to the 0th power. The result is just a 1, because anything to the 0th power is equal to 1. All right. That's nature of numbers. If I take x plus h and raise it to the 1st power, the result is going to be x plus h. All right. I'm actually going to move this over just a smidge. All right. The coefficients of the x plus h are the numbers 1 and 1. I'm going to have to zoom in a little bit to get there. All right, so I'm going to write the numbers 1 and 1 below the 1 for x plus h to the 0. All right, so you can see, I mean, it's not your classic definition of a triangle, but it's triangular in shape. All right, the 3 numbers there should form what looks like a triangle if a triangle was made out of numbers. All right. So then next up would be, if we're increasing the power, x plus h squared, which we've done a bunch of times. And we know that that's x squared plus 2xh plus h squared. All right. The coefficients are 1, 2, and 1. So what I would do is I would continue constructing my triangle by putting the numbers 1, 2, and 1. All right. It's still in a triangular pattern, but now I can start actually recognizing a relationship. First off, the first and last values are always equal to 1. All right. So if I wanted to create the next row of Pascal's triangle, I know it would have to start off and end with a 1. All right, just to follow that trend. But also another nice consequence of it is if you take the sum of consecutive values, it gives you the next entry in the row below the entry that you're in, or the entries that you're in. So for example, if I take the sum of 1 and 2, I'll get a 3. So I put a 3 here. If I take the sum of 2 and 1, I'll get a 3 again. I'll put that 3 there. Still in that triangular fashion. Now you can keep adding rows to this, but if we work backwards here, what this is telling me is that the coefficients of x plus h to the third power should be 1, 3, 3, and 1. All right. Now we already know that because we already did the expansion. But if I bring it back out, you can look and you can see 1, 3, 3, coefficient of 1. All right, the 1 in front of the h squared, the cube, sorry, that understood 1. All right. So we have a method by which we can come up with the coefficients. Now what I want to do is come up with the variables. All right. So if I variables and also the associated powers. So what I'm going to do is I'm going to take us back to x plus h squared and take a look at what's actually happening with the powers there. I'm going to write it in a slightly different way. I'm going to kind of expand it out a little bit, give a little bit more room for some things, a little less room for others. All right. So one thing you might notice is that the power for x started with a 2, then the power disappeared, but it didn't really disappear. It's still there. It's just a hidden power. This x here actually does have a power. That power would be a power of 1. All right. So we're decreasing our powers from 2 to 1. And then I put a little space here because you could then assume that the last entry would have a power of 0. So there's really a hidden x to the 0th power there. But we know that anything to the 0th power is equal to 1. So if I did 2 to the 0th power, if I did 10 to the 0th power, if I did a to the 0th power and added a slider, no matter where I put my slider, a to the 0th is always equal to 1. All right, so anything to the 0th power is going to be equal to 1. This just disappears in the full expansion because we tend to simplify our expressions, but that's really what's happening. All right, so if we follow that idea where there's a correlation between the power in the given expression, x plus h squared, and the starting power for x, then we would know that x plus h cubed would have to start off, I'll use green, with an x cubed, decrease to x squared, decrease down to x to the first, and then decrease down to x to the 0th. All right, all because this power needs to correspond with this power. All right, but then a natural follow-up question would be, well, what about the h's? Well, looking at the h's, I see that I'm ending with that same power of 2. And if I work from right to left, my second term from right to left is an h, which is really an h to the first. So then we could assume that this one must have been h to the 0th in order to complete the trend. So if we follow that same idea, we'd be saying, all right, on the right-hand side, let's start with an h cubed, because this is the power of 3 function, decrease down to h squared, h to the first, and then h to the 0th. And then you just have to put some plus signs in and you're done. All right. Yeah, you have to simplify a little bit, but not a whole heck of a lot. All right. So this would become x cubed, because the 1 would be irrelevant. The h to the 0th would become a 1, plus 3x squared h plus 3xh squared plus h cubed. All right. And that's what we got before. All right. It's the same expansion. I'll show you another one in a second, just so you get the idea down. But it only took so long to do because I'm slowly and carefully explaining it. But it's actually pretty quick. All right. So the whole idea is to efficiently expand a binomial rather than, I mean, because you imagine if I gave you something like x plus h to the 8th power, and you were to do it the same way we did it before, it would take forever, right? But it's not the case here. With Pascal's triangle, it'll go much quicker. I'll get to the question in a sec, but let me just do x plus h to the 4th, just so I can give you another run through on the process. All right, so we have x plus h. Let's say we're looking for x plus h to the 4th. That would mean that we would need the next row in Pascal's triangle. One thing that is a little kind of on the weird side is that the power of 4 corresponds to the 5th row. That's only because it's offset by 1 unit, because we start off with the power of 0. All right, so I would construct my next row starting and ending with a 1, taking the sum of consecutive values along the way. So 4, 6, 4. All right. Those would be the coefficients of my expansion. So when I'm looking to expand out x plus h to the 4th, I would then write 1, 4, 6, 4, and 1. Then what I would do is say, okay, I know I'm going to start off with x raised to the 4th power. So x to the 4th, then x to the 3rd, x to the 2nd, x to the 1st, and x to the 0th. All right, all we're doing is writing them in decreasing order in terms of their powers. And then I would work from right to left, starting with an h to the 4th, h to the 3rd, h to the 2nd, h to the 1st, h to the 0th. Pop in some plus signs, simplify just a smidge. Basically, I'm just dropping the powers of 1, and anything with a 0 power I'm disregarding. And this would be your expansion. All right, actually, I said I was dropping power of 1 and I missed one along the way. All right, and that would be your simplified form, which is a whole lot easier than saying, all right, I'm going to take x plus h multiplied by x plus h, then multiply that answer by another x plus h, then multiply that answer by another x plus h. All right, and this is something that you're going to need to know. All right, so it's you know, we don't want to gloss over it. All right, question? I see a hand raised.
Oh, yeah, I kind of already answered it in itself, basically. Like, so it's just going from decreasing to increasing order.
Yeah, decreasing left to right for x, and decreasing right to left for h.
Okay. I mean, I still feel like, I'm gonna be honest, I took a other calc class back in high school, and it was something. Actually, I'm pretty sure we'll probably just get to it, so I'm just gonna leave it at that.
Yeah, there is another layer to Pascal's triangle. So if that's what you're thinking, then yeah, we're going to get there. So on the next page, we got a couple more examples, but the good news is, well, it's good news, bad news. One of them's really easy because it's a linear function. This is what we were talking about before. It's a linear function. So I know my answer is just going to be whatever the slope is. So 4. I mean, you can do the work if you want, but I would imagine you don't. I wouldn't want to. So, I mean, you do the work for practice, but you don't necessarily need to do the work to get the answer because it's whatever the slope of that line is. But for part B, that's the alternate difference quotient. So we want to take a minute and go through that. That's actually a whole lot easier to handle in terms of the setup. There's a lot of craziness going on with the setup of this difference quotient, but the setup for the alternate difference quotient is actually very simple. The problem is sometimes it can involve some obscure algebraic topics along the way. All right. So if I know that my linear function is going to give me an answer of 4, then going into the problem, at least I know what I'm aiming for. So that's good news. All right. Now you see that this component here says f of a. We have the f of x already. They gave that to us. I need f of a. So f of a, well, f of anything is whatever the function would be if you replaced x with whatever the anything is, right? Whatever is contained within the parentheses, you're replacing x with that. Now here it seems very simplistic. It's like, all right, so really, I'm replacing all my x's with a's. All right, oddly simple, but that's what it is.
Wait,
Right?
Professor, you lost me there. That made no sense. Like, shouldn't we? Can you just re-explain it? I'm sorry.
All I'm doing when I'm finding f of a
Mhm.
is replacing every x in the original function.
With just
With an
a?
X. Yeah.
Oh boy. Okay.
So my original function is 4x minus 7. That's f of x. My f of a is going to be subtracted from that. So 4a minus 7. I'm going to take that and divide it by just x minus a. We're going to simplify first, of course. So 4x minus 7, little distributive property here. I'm going to get negative 4a plus 7. I'm going to take the negative 7 and positive 7. They're opposites of each other, so they'll cancel away. And I'll be left with, on top, 4x minus 4a over x minus a. We notice, hopefully, the common 4 that can be factored out. And when we factor that out, we're left with just a 4. All right. Now, it won't always be the case that your two difference quotients will give the same answer. But for linear functions, they will. All right. When you get to other types of functions, it's not going to happen. All right. You might have elements that are similar, but it won't be identical like we see here. Right? But what this gives us is a license. Whenever we see a linear function, we jump right to the answer. We already know what the difference quotient will yield for a linear function. It's going to be whatever the slope of the line is. So we just take that and run with it. Because you're paying the piper when it comes to the more complicated ones. So take the gift when you receive it for the linear function. Don't do unnecessary work. All right. So that's something that hopefully you'll recognize when the time comes.
I have a question.
Sure.
The 4 is the slope of which line?
The original line, f of x equals 4x minus 7.
Okay, that's what I thought. Thank you.
No problem. Now, for number 5, that's not a line. We have variable slope when it comes to curves. So, there's no shortcut there. We have to just dive right in and go for it. However, it has a power of 3, and we've already evaluated what happens when you have a power of 3, right? Whether you're using Pascal's triangle or you're distributing it out by hand or you're just memorizing the expansion, any which way, you should have the x cubed part of it already accounted for. Right? So we start off again with our f of x plus h, which is what we would get if we took our original function, replaced every x with an x plus h. We now know from experience and experience, the greatest teacher, failure anyway. So experience is a good teacher, because what'll happen is you'll see the same thing over and over and over again to the point where you just remember it. All right. I'm not going to say it's ever going to be as simple as multiplication tables, but if you ever found that to be simple, but it should be something that you can look at and say, okay, I know this because I've done it 1,000 times. Right. And so this is one of those things. We have x cubed plus 3x squared h plus 3xh squared plus h cubed. Why? Because we just did it, 2 problems ago. Twice. So use that information, use that knowledge to your advantage. So I'm going to run through with the -5. The -5x cubed minus 15x squared h minus 15xh squared minus 5h cubed, and then plus the 2 that was already along to the right. So that's our f of x plus h part of it. Then we're going to take that and chuck it into the actual difference quotient. This time I'm going to copy it before I highlight it. So we have f of x plus h. They told us f of x. Now we just have to assemble it all.
I have a question.
Yeah.
Never mind. I don't think it. My question was originally, would the 15x squared h cancel out the one in the middle? But and I don't see the sign, so I kind of answered my own question.
All right. Sounds good. All right. So from this, we're subtracting off the -5x cubed plus 2 over h. And again, we know from experience that anything that doesn't have an h attached to it's going to cancel away. Then we have that common factor. Oh, I missed an h along the way. Apologies. All right, so and it's just a matter of canceling the h's and we have it. So it's just whatever we have here. That would be our final answer. All right, so that would be it. But you could see if you were to compare this to the other problem that we did that involved the power of 3, that we did it a lot quicker. Not because I rushed it or anything, but because we were able to rely on some prior knowledge, right? And that's going to happen. And that's one of the things about the difference quotient that allows it to become an easier thing along the way, to the point where, you know, a whole semester will go by, just enough time to forget a whole heck of a lot of the course material. But then you'll walk into a calculus class or log into a calculus class, and the teacher will start talking about the difference quotient again. And you'll be like, all right, I know we talked about this last semester, and then it'll all come flooding back and you'll hit the ground running. Right? Well, because of my great instruction. No, it's everything's easier the second time around. Right? So that's really what's happening here. All right, because this is the foundation of some pretty intense calculus concepts that you're going to get to in the next course. All right. But we also want to do it with the alternate difference quotient. By the way, the word of the day is experience. I said that enough. So the word of the day is experience. And you know, I've gotten a little cynical in my old age, so I couldn't help, but take note of all the phone numbers exchanged over Zoom. And all I would say about that is I hope that's not for the purpose of sharing the word of the day with people who might have logged out of the class and not have been paying attention. Because if I get the idea that that's happening, then this word of the day incentive bonus opportunity will disappear. Right, so let's make sure we do the right thing on that front. Right. So f of x minus f of a over x minus a. Negative 5x cubed plus 2. That was what was given to us. So we have that already. We have it and we need it. So we're good to go there. We need f of a. So that would be what you would get if you replaced all the x's in this expression, in this given expression, with an a. Right? So everywhere there was an x, there will now be an a. So I replaced this x with an a, I replaced that x with an a, and we have that new expression. The setup when it comes to the alternate difference quotient is as easy as it could be. All right. To the point where you start questioning whether you're doing it right because it can't be this easy. That's kind of what you walk away with. All right. Now you distribute it out. I got my -1 here. Run it through. Oops. So I'm looking at -5x cubed plus 2 plus 5a cubed minus 2. The 2 and the -2 should cancel away, and they do. So now I have a -5x cubed plus 5a cubed over x minus a. I can factor out a 5, but it would actually be in our best interest to factor out a -5. Because I notice on the bottom here, my x has a leading coefficient of a +1. So if we're going to be able to simplify, I want to eventually get this x to have a coefficient of a +1. All right. So in order to do that, I would pull out a -5, and we get x cubed minus a cubed. And here you're at the mercy of prior knowledge also. All right. What we're looking at here is a difference of 2 cubes. Difference of 2 cubes is a factorable expression. All right, good old college algebra. It's like memorize this rule and then you use it once all semester and then what? You know, it's a recipe for forgetting it. So here's the rule. You know, it's an algebraic concept that will come up repeatedly, just at odd intervals. It's like, all right, now wait another 6 months before this one comes up again, but it'll come up. You know, hopefully you review it enough times where it kind of sinks in. But anyway, the rule is if you have an expression in the form of a cubed minus b cubed, it's equal to a squared plus ab plus b squared. Oh, I missed an entire factor. Sorry. A minus b. All right. So that would be your rule. I was like, why does this look funny? Because I didn't write the correct rule. That's why. All right. So this is the rule for a difference of 2 cubes. So what we want to do is match that up to the expression that we have and follow the model. All right, in order to factor it. It gets a little dicey because you're looking at, you know, like the rule has an a in it, and so does the expression that we're working with. So you just got to kind of keep it straight. But that's just an organizational thing. Because I'd look at this and say that x is taking on the role of a, and a is taking on the role of b. All right, so in this expansion, wherever I see an a, I'm going to replace it with an x. And everywhere I see a b, I'm going to replace it with an a. All right, so that's old school, but you know it's a method that works, but you need to have access to the rule in order for it to make sense. There are shortcuts for it, but you know maybe that's you know for a different time and place.
Professor?
Yeah.
If it's like a cubed plus b cubed, can you just break that one down too?
Yep. So for the sum of 2 cubes, we have another rule. If it's a cubed plus b cubed, it would be a plus b times a squared minus ab plus b squared. Okay. There is a little nifty shortcut for remembering the sign distribution. I saw it in a textbook once. It was kind of cool. It's SOAP. Same, opposite, always positive. All right, so the first sign in the expansion is the same as the one you started with. The second one is the opposite, and the last one's always positive. So the first one is the same, second one is the opposite, and the last one's always positive. If that's helpful, great. If not, then pretend I didn't say anything. All right, so that factoring technique allows us to go a little bit further with this expression. So just kind of going back to, you know, what we're doing all this for. So I had that -5 there. That x cubed minus a cubed now gets replaced with an x minus a times x squared plus xa plus a squared all over the x minus a, which allows us to cancel the x minus a's, which gets us to our final answer, which actually looks nothing like the other difference quotient, -5 times x squared plus xa plus a squared. That's poor quality A. You could distribute through the 5 if you want or not. It doesn't make a difference. So nobody's going to lose any sleep over that, except, you know, maybe a teacher down the line who just kind of like hates life and everybody. But, you know, that's not me, not yet anyway. So, but you look at the solutions here where for the ordinary difference quotient, you get this answer. And for this one, it looks nothing like that, but that should kind of make sense because the A means something different for the alternate difference quotient than it does for the ordinary difference quotient. So it shouldn't be surprising that you get a different looking answer. It all goes back to the theory, but what I was mentioning before, it's kind of hard to keep track of the theory you know, with all the algebra that's going on. The algebra is very distracting, you know. So if you have the time, try to internalize the theory. I mean, at least before you get to calculus, it'll help. It'll help you understand the concept of the derivative more, and that'll kind of propel you forward in calculus. All right. So I just wanted to touch on one more thing before the end of class, and that's inverse functions. We're not gonna spend a whole heck of a lot of time, right? Only like 5 more minutes or so.